recent deep neural nets. So, in fact, as what I'm trying to normally explain things, I start from history, because history tells you a lot of the background reason of why now. And then I'm going to give you a very, very quick survey about a few recent trends. So this is a history of starting of the definition of AI and definition of machine learning until 2000, which just wrapped about 10 years before now. So the first paper is from Alan Turing about this paper called Computing Machinery and Intelligence. The reason why this is important is the Turing test. He proposed how to tell if a computer has intelligence. That's the famous Turing test. Actually, feel free to check it out. It's a very important test. And then later in 1956, there's this AI workshop in Dartmouth created the definition of AI. And then in the 1950s and the start of machine learning, most people in the field kind of agreed on is from Samuel's checker player. And it's not using rule-based approach to solve checker, but it's using historical checker play histories, the data-driven. This is the first data-driven formulation, and people normally think this is the start of machine learning. And this is the start of AI. And then later in the 1950s to 1969, actually neural nets kind of dominating the majority of the machine learning research, or AI research. And then in the 70s and 80s, people kind of found the neural nets is so difficult to work with, and the majority of the field moved to the expert systems, or the rule-based kind of logic-based inference engines type of work. So the whole idea is we want to equip the AI system with a lot of knowledge. That's a fundamental idea, different from the other previous neural nets, but more the functional estimator. And in the 1990s, actually there's a popularity of neural nets, which is especially is the creation of convolution neural nets and recurrent neural nets. So actually the most important two type of deep learning models using now, CNN and RN, were invented in the end of 1990s. And then in the 2000s, it's 2000 to 2011, people kind of abandoned the neural nets and kind of dominated by the machine learning research was dominated by support vector machine, kernel machine, graphical models, sparsity, sparse coding, matrix factorization, semi-supervised learning, transfer learning. There are a lot of work at that, all structure output prediction. So maybe you think DN is now, actually the very, very important modules, CN and DN were invented, like convolution neural nets were invented in 1990 in the famous LearnNet 5. And the task is for hand digit recognition. And RN is first invented in 1997 by Professor Jürgen, and it's called long short term memory in that paper. So why in the winter, and that two important modules was already invented in 1998 or 1997, right? Why they are popular now? So the reason why in the 2010s is, first of all, it's a non-convex object optimization task. And during the 2010, the whole field prefer convex type of formulation. And also, the deep neural net needs a lot of tricks. It's very difficult to play with for the newcomers at that time. And also, there's no good computational platforms to train those models. And also, it's very difficult to perform theoretical analysis. All right, then you all know in 2012, the AlexNet got a dominating win in the ImageNet competition. So this competition in the 2010 and 2011, the error rate is about 0.28. Then in the 2012, it's dramatically improved into 0.16. It's 10% of improvement. And this is true revolutionary improvements, right? So you normally work on papers about 1% of improvements or 0.5% of improvements. Those are incremental improvements. And this is a very solid, big improvement. And this is the reason why got whole deep neural networks and all the related research got really popular, and people got to put their attention, especially industry giants, Google, Facebook, all those bigger IT companies started to realize this is ready now. And then start from AlexNet, and then gradually until 2017, and this is almost a human performance, about 0.02 error rate. And there's a lot of this improvement in the middle, but the majority of those the models are actually or convolutional neural network based. All right, and then after this big breakthrough in 2012, and people started to not call it neural net, started to call it deep learning. And then there's this DeepMind company who did a lot of very, very cutting edge work to push deep learning to more complicated intelligence-focused tasks. For example, especially this really big breakthrough in the AlphaGo in 2017, they used deep learning to truly show reinforcement learning can achieve something not being able to be achieved before in this Go game. It's dominated and win all the Go masters in very solid wins in 2017. And then, of course, now there's AlphaStar. There's a lot of different variation of this deep learning-based reinforcement learning engines kind of dominating a lot of games. Not just the Go games, StarCraft. There's a lot of current very similar breakthroughs, but they're all following the AlphaGo, kind of that framework. And the other breakthrough is the 2018 from Ian Goodfellow, doing this very novel method doing generating samples called generative adversary network GAN. So this is also a very novel, very revolutionary type of work because generating good quality images that cannot be generated before. So you can tell, in the end, in the current era, the true improvement truly needs dominating solid advancement compared to before, and they're not always also they're all mostly also pretty novel. Okay, so why this type of method are breakthroughs? So in fact, if you think about starting from the 1950s, and Aaron Turing proposed this Turing test, trying to see, can we make computer intelligent? And then the idea is, what do you even mean intelligent task, right? The simplest task is humans' vision, humans' ears, humans' understanding. So can we make computer perceive the world, capture signal from the world? Speech recognition, object recognition, and these are actually the current focused task and the current computer can do very well. And recently is the deep learning moved to the next step, understanding the world to give really solid results, like machine translation, and but not yet in text semantic understanding, and even more interact with the world. So the state-of-the-art computer agent interact with the world in those game situations. but it's not very solid yet in the true real-world situation because the uncertainty dominates in the real-world situation. So it's not there yet, but people are trying to get there. And then later, so can we make computer able to think, able to reason, able to imagine? So the reason why GAN is so important is you can think about it gives the computer a certain level of imagination because it can generate images. I'm going to show you pictures later, follow some kind of styles. It's a really cool work, and in the end, it's more like an analogy type of intelligent task. But to be honest, even a 3-year-old or 4-year-old can do the analogy and the imaginer work pretty well. And computers still have a very long way to go in this type of more advanced or more higher level of intelligent tasks. But we are really doing very, very well on the perception level of tasks. Object recognition, speech recognition. That's why maybe you have Alexa at your home. If you interact with the Alexa, it's most likely can recognize your speech nicely. But if you ask a little bit difficult question like, can you play a good song? Some more blurred, not precise type of retrieval or needs certain level of understandings, Alexa cannot do very well yet. The reason is it handles the speech recognition level very nicely, but it cannot, still not yet, the text semantic understanding, that level of intelligence still needs to be improved. But I think people are getting there. Okay, so this is the trend. I just did a very quick summary of the trends, and I will put quite some work in CNN because your homework it's about convolution neural nets. So I'm going to skip over all the rest like RNN, pre-training, autoencoder decoder, memory network, all those very, very quickly. Okay, so how do we, there's so many work now. How do you think about each work using some kind of structure? Again, so we're using our nutshell idea. So you can always, when you see a new paper, a new work, think about, is this a novelty in the task, or is novelty in the representation, or the novelty is in the loss function, or the novelty is in the optimization or search, or the novelty is on the model, the properties of the model. So that's why, that's how I split the trends into those 5 different sections. So there are a lot of new tasks. So what we focus on is mostly prediction tasks, right? Regression prediction, classification prediction. There are a lot of revolution or new things in the current trend is I'm not predicting from X to Y. I'm maybe generating X that's similar to a corpus of existing X. X, that's like image generation tasks. There's also reinforcement learning, not just to predict AY. I'm actually interacting with an environment to predict a sequence of Y's, and there's a relationship among each predictions. There's also reasoning task. I'm making analogy, so that's not directly can be put into the current prediction formulation we already reviewed. And also the data type of inputs. So the majority we covered is numerical type of inputs, right? So how do you handle string data, graph data, time series data, set data? And that's in some kind of reformulation too, beyond the current multi-layer perceptron we reviewed last time. There are also architecture design, right? So there's a lot of novelties. So actually CNR and the majority of the novelty is in the architecture design. It's the model design. And also training, search. So can you have a new loss function? There are a lot of work is about a new loss formulation. And can you have new optimization tricks? And can you even learn, can you scale up to make use of distributed computer architecture as well? So there are a lot of tricks in different dimensions. And there's also the last one is the current, more CS focused. So as we always said, machine learning, the training phase is, in the end, it's like a coding phase. You're using data to code a software. The model is a data learned software. So we can call this software 2.0. So whenever you think about that software, there are a lot of things we have handled in the computer science can be used there, right? Can you how to trust that software? How to guarantee that software is safe? How to guarantee that software doesn't make errors? How to understand that software? So there's a lot of things we use to do work on software engineering or software testing can be all applied or extended or adapted in this type of model, data learned software. All right, question here, 5 things. I mean, you can always think of whatever new method and put them in here. Is a novelty only one or a few? Okay, so because I have so many slides, I'm going to do quickly today. So like I emphasized in the beginning, like it's also the last part of the last section, the whole neural nets, we have to really remember it's a block-based formulation. The whole operation of forward and backward is only related to input of the block, output of the block, and local gradient related to the output versus the input, those partial derivatives. And you don't really need to handle other blocks, just my local blocks. The input, output, local gradient, you can perform forward and backward. And each one of them, that's the only thing you need to know. Then this makes the whole thing totally composable, right? So in the end, a lot of different neural nets you can think about, they're just Lego building. Because what you need to care, it's just input, output. How do the output being generated from the input? And then how do the backward, the gradient from my future layers and times my current local gradient and directly pass to all the layers before me. And I don't even need to worry anything about other layers as long as I can do the forward operation and the backward gradient propagation operation. That's it. That's why it's extremely modular, and that's why I could see as people in computer science like it a lot, because this is so like object-oriented programming, right? Here we can use data to learn each block, and then you just put them together. Of course, there's a certain requirements, maybe match of the output to the next layer's input, but those are really similar to the Lego build, right? As long as they can be matched, then they can be put together. So that's the whole thing, and that makes it very, very, can be adapted very nicely, can be composed into many complicated tasks, and the gradient descent make it also extremely adaptable to adjust, as long as you can adjust local gradient, the signal from the future, the task oriented can be all the way back propagated to adjust all the modules through back propagation. So that's why it's very, very versatile, and there's a lot of variations. So I will cover the majority is the novelties is either in the input and the output, or the losses, or the architecture, or the software 2.0, how do you work with it? So I don't actually review about optimization tricks at all. So optimization, there's huge literatures, and also I shared you with one of the to read. There's a very good archive paper summarize almost all the tricks. It's also one of the very popular research topics people trying to advance the state of the art. So what I'm covering today is mostly in the other four. Okay, so the first one, because it's related to your homework, so let's just cover is the network topology. So the first trend, actually it's not a trend at all. Yes, it's dominating, but it's not that new. It's invented in 1998. So this is the 1998 version, LearnNet 5, and this is the AlexNet version in 2012, which won the competition and brings back the neural network hype or revolution. Okay, so what is convolution neural net? It's actually extremely simple. The whole idea of convolution neural nets is this figure. This, and this. So they are all bird, right? Just one bird. This bird, if I want to recognize this bird, I really don't need the whole image at all. What I need to focus on is over here. However, I don't even need to focus there. And the bird can be here, can also be here. So that's the whole idea of object recognition, which called two properties here. It's locality and translation invariance. So the object tend to have a local spatial support, spatial pattern. Translation invariance is object can appear to be independent of the location it appeared. It's not because in the middle this is a bird. It's not about that location at all. Of course, there are certain, maybe sky obviously on the top, but a lot of object has that property. The location doesn't matter that much. Okay, so the whole convolution neural nets is to explode these two properties, locality and translation invariance. In fact, there are many different type of data has similar properties, like audio data or text data. The speech signals also has this locality and translation invariant feature. So, the multilayer perceptron, so this is actually the whole image. In fact, this is all my X. Everything here, it's the full image is my input X. If I'm learning a multilayer perceptron, I have to have this size of a W, right? For that level of W. But I don't need to do that because my objects are super small, actually much smaller than the whole image. Then you just have a much smaller filter to check it, to capture it. And this is the whole idea. So I want to check, is there a bird here? Is there a bird here? And I don't need a W or a weight matrix to cover the whole thing. I only need a size of the W cover this smaller mean window. That's the local filter. And also because the bird can be here, the bird can be here too. It doesn't matter. It's not because here it use weight 1, here it use weight 2, no need. As long as it's a bird, I use the same filter. So that's why I'm using same weight to check, is this a bird? Or the same window weight, check, is this a bird? So this is exactly convolution unit. It uses a very small window of filter of W. In the end, it's just still a W. You perform W transpose X, and that W is only applied to a local region of the image. And it applied again and again across different positions. And the weight is always the same. So this is what we call local weight and plus weight shared. Local weight is to fulfill the locality property, and weight sharing is to fulfill the translation invariant property. Question about this?
How do you know the dimension that you're scanning? Let's say here you have 3x3.
Good question. So you normally do not know. So this is one of the hyperparameter in the convolution neural net you actually need to know. You need to design as a designer. Okay. All right, so this is actually, I copied someone's slides, just trying to show you. If you want to recognize this is a cat or a dog, if using multilayer perceptron, you just put all the pixels and you concatenate all the features into a big vector, and then you do multilayer perceptron. And this is the multilayer perceptron way. And this is the most basic classifier. And you just keep propagating the signals, and then you try to recognize, is this a cat or a dog or a human, or the class labels. And to emphasize, because I showed you the whole bird before, right? But it's not just bird, actually components of a bird, like in this case, is the bird, this bird, pig. It's also a fixed. It's a very fixed local pattern. And how do you recognize it? The whole idea is I'm designing a detector to detect it. I'm trying to apply a detector to detect, is there a bird mouth there or not? Question about this? It's actually just W transpose. I'm designing W transpose X, and X is just a window, part of my full image, a small X sub window, then goes into the sigmoid function we always mention, again, summation function, then the squashing function. All right. Okay, so this is about locality. And then the translation invariance is, that bird is more close to the top of the image, and this bird is more in the middle, but they both has very similar beak, right? And then how do you search for it? And then you share the parameter, you detect the beak, use the same type of weights to perform the operation in this position too. And similar, that means, yeah, they're doing almost the same thing, so that's why I'm using the same weight filter to perform W transpose, that W, as transposition X plus the B, the same Z, and then Z goes to a squashing function, even though this is in the middle of the image, but it's the same WS as before. And they are different XS, but the same. So let me the first in the upper region, and this is more in the middle region. All right. So, and there's a third property is very important. Is if you subsample an image, it will still look like the bird. It will not change the object property at all. And this is really defined by the continuous property and spatial local continuous property of the images. If you do subsampling, it will still give you an image, but just a lower resolution. And because this is a lower dimensional input, right? And we actually told you before, if the P is too large, so this converted, assuming this is P, and this goes to XP prime, and P prime is much smaller than P. When P prime is much smaller than P, what does this even mean? The W, because this is a much smaller input space, right? And you need less parameter to make a decision. When you need less parameters, you need less number of examples. It's just easier to make a decision for this case. All right, so this is subsampling. Easier on the subsampled, more hopefully pattern more clear set the image. Okay, so we can subsample the pixel to make image smaller. So yeah, and then this actually means less parameters from here to make a prediction this is a bird. From here, that needs more parameters because a larger P. Sorry, I will shift my handwriting lower in the shared version. All right, then this is exactly the whole CNN. So convolution implements the locality and translation invariance operation, and then max pooling subsample the images to make it smaller. And you can repeat this operation multiple times. And then for the generated much smaller image, you just stretch it out with all the pixel values into a vector. And from that vector, you feed into this multi-layer perceptron we learned and to perform classification. Is this a dog or is this a cat? In fact, this mostly use the softmax function we learned in last class to predict it into one of the class that in our output space. So this is the Y and this is the X. And it uses cross entropy loss like we said last time. With the software layer, go to the Y prediction, Y hat, and then use cross entropy loss to back propagate, shrink all the layers here. Cross entropy or negative log likelihood. All right, question of this? Again, locality, translation invariance, then subsample it into a smaller image, and then do it repeatedly multiple times, and then flatten it. Check.
Does the size of the object relative to the image
Design.
subsampled it matters?
Yeah, there are a lot of design. What is the proper convolution size? So if I have it. Okay, so this you already know, the property one, local translation invariant and subsample. So I want to skip this really quickly. Yeah, so I want you to, so this actually to be I'm going to answer your question later. So this is the first W. So assuming I'm trying to detect, so this is a W I'm learning, the W1, and this is a W2 I'm learning. There might be multiple type of pattern I'm trying to learn. So assuming I'm trying to learn this pattern, this is the first edge pattern I'm trying to learn. And another type of pattern, what I'm learning to learn is this. So hopefully I use back propagation. I already learned good W. And this is the first W can detect this pattern. And this filter can detect this pattern. Why? So what do I even mean? W times WS time transposition. So this is my W. W1, and this is the part subset. And this is my X subset here. So the whole thing by applying convolution neural nets is to do this. So I'm applying that W to perform WSXS. W inner product, W1 as transposition, then this means the inner product, X the current position, subsets, just to show you. So when you're applying this with the inner product, what do you get? This is my W and this is my X. It's inner product, right? What do you get? 3. Okay. But I actually do not know. How could I even know it's here? I have to apply that mouse detector or beak detector all over the place, right? I'm applying this filter on this position and then on the next position, next possible position. Assuming I'm only move one, shift one. I apply on the second position, I got a -1. I applied it on the third position, so on and so forth. And you just keep continuing. You're going to get, sorry, it's a little shaky. Yeah, so this is what you're going to get. You apply the filter on all the possible positions by doing small shift. That shift size is called stride. In this case, we shift that window with only stride size 1. And then this will convert it. So this is the last applying that filter, we're going to get -1. So this converted a 6x6 image into a 4x4 activation output. And you can actually tell the higher values, this value is really high, right? This value is also pretty high. Why they're pretty high? There's two values. Yeah, because my filter is doing what? My filter is doing this. That's exactly the two locations with that pattern. It really detects the specific pattern my filter trying to detect. And this gives me high values, means the pattern is there. And this is totally just a convolution neural net, the basic operation, nothing special. Question about this? All right, but there's still a lot of other numbers, right? Yeah, this is high and this is high. It's still pretty messy. Yeah, so this is trying to show, and it's showing the first filter, and yeah, so that's exactly what I try to see. 3 and 3. Okay, so you can apply the second filter. So do the same thing. The second filter trying to get this type of pattern, and look which one give you high values. So who is 111? The only thing is here, right? So in this image, the only pattern actually matches my filter 2. It's here. You do the same thing. You just apply it at every possible locations, and then what you're going to get, this value is high. This is the only pattern actually matches to that filter. All right, so we normally call this called feature map or activation map. And this is a 4x4 image because you're applying this 3x3 filter operations. It can only be applied in this case it's 4 times. That's why you converted 6x6 to 4x4. All right, so but in fact, the colorful image you're going to handle in the homework has 3 channels. So then you actually have 3 this type of matrices, 1, 2, and 3. So in the case of RGB, there are R channel, B channel, and G channel. There are different channels. And you need to design the filters. The filters, each of those window detector also need to have 3 channels. To reflect the image property, have 3 channels. And so why we're doing so we already said because the local and translation invariant properties, right? So compared to the fully connected network, let's see how many weights do I need here if I'm doing a fully connected image, just do a multi-layer perceptron, because this is a 6x6 image, right? 6x6 size image. The size of the input is what? 36. So this is the multi-layer perceptron, and then if the middle layer is, you're assuming it's the number of filters, the hidden unit size h, then the first layer is the size of the weight is 36h. But in here, so assuming h equals to 2, so there are 2 filters, and then this means there are 72 parameters in the first layer. But in the convolution version, how many do we have? How many parameters? In the convolution version, that's our W1 and W2. In total, how many parameters here? 18, right? So it dramatically reduced the number of parameters. This is actually 9 plus 9, holding 18 parameters. So the first purpose in the end, reduce the number of parameters, capture the properties of the task well. So this is all like kind of repeat, try to tell you, and then I want you to read by yourself. Yes. How do this even local means? Yes, less parameter from that local W, and then with the weight sharing with even less parameter, share with makes the parameter even smaller. Then let's talk about the pooling step. So we already applied our image with 2 different filters, right? And this is what the feature map is generated. We actually know in the original image, this pattern and this pattern appears twice. And this pattern appears once. And like we already said, right, in the image case, if you do subsampling, just the strong signals is enough to represent the final object class. And in this case, to be honest, I don't care about that, the other values. What I care is the strong numbers, right? Strong numbers. What operation leaved strong numbers, removed the weak numbers? What operation, mathematical operation, leave the strong numbers and remove the weak numbers? Max operation. It's actually this. So the whole thing is, because you can do subsampling, right? I only care about the small region, the strong numbers, the large values, because large value means I detect that pattern. I'm doing max. This give me, I only use 3 from that local region. And this also use 0. We're trying to max out, only leave out the strong response to my filter. And I only care about the strong response in that local region. All right, then you do this. This is what max pooling means. And because I don't care about other at all, what I care from the first filter is who matches with the first filter's pattern. This one and this region. And this not. This is less not too. And for this, it's very clear this part matches that pattern, and using the max operation, we got a much clearer representation and also much less number of numbers to process. So that's the max pooling really does. Question about this?
What if there are more than one maximums in all?
More than one max? Good question. Let's handle that later. Yeah. All good questions, but let's handle the intuitive first step first. Yeah. Okay. So in the end, convolution and max pooling, it just use local window to detect, do I have a local window size pattern, and use the max pooling to get stronger responses of each filters out. And this is what you get after convolution and max pooling. And it's very clear, these 2 sub-regions matches with my filter 1, and this region matches my filter 2. And then you can do other complicated, assuming we're doing maybe a big X or maybe Y. Yeah, in this case, maybe it's a little bit weird. So assuming I'm trying to recognize handwritten digits Y, and this is what I wrote Y. Okay, so tell me, how many local filter do I need? Just based on what I've already discussed. How many filter do we need? Only 3. This pattern, that pattern, and this pattern. That's it, right? It's the whole idea. How many filter do you need? It depends on your data, depends on the task. I'm doing Y, there are only 3 continuous or 3 clear patterns, right? If I'm doing a more complicated, give me an example. Handwritten digit recognition. 8. Think about 8. Think about 8. How do you recognize 8 if I'm doing this type of local, this type of shape, right? So in the end, it's not complicated at all. It's more like a piecewise decomposition of this, because that's how your filter located, how your filter arranged. All right, okay. So yeah, each filter is a channel, or you can think about each filter is a sub-pattern detector. And there's some easy, like a case of Y, or maybe 1. Yeah, it's much easier. But there's some much harder, like a case of 8. All right. Yeah, so let's summarize. And the max pooling, as I said, they give you a smaller and sharper image. The sharp is in the sense of detecting the pattern. Okay. Yeah, so this has a little bit flattened, so try to read it. So flatten is really just concatenate. You just concatenate. This is in an image. This keeps the spatial relationships. In the flatten, you actually remove it. You don't need to care anymore. You just concatenate it into a long vector. This is what we meant, flatten. And then you do this flattened output representation, you feed it into fully connected multi-layer perceptron we learn, plus a softmax layer, and to predict. So this is what I try to, actually this professor wrote it, I think it's really nice, and you read by yourself. And the whole thing is, you don't even need to understand details at all. You just need to design the pooling size. So what's the size of the max operation you perform? Is it 3 times 3 to go to 1 or 2 times 2 go to 1? The range of max operation, that's max pooling. Convolution is the kernel size, the filter size. How many detectors? How many detectors do you need? Like the question I just asked you, we showed only 2, but it normally not enough. Has only 2 detectors. You normally need much bigger number of detectors, and that's the number you need to design. And also the window size, right? I showed you 3 times 3, but there may be cases, actually, it depends on the data, you need to have bigger windows. And also layer by layer, how many layers of convolution, max pooling, you repeat this. These are all part of the design. All right, and then in the end, after you have, then you just feed into multi-layer perceptron layer, which is extremely lazy, with a flattened layer. Flatten, that's why you need to understand what's flatten. Then go to, actually here, the dense, fully collected multi-layer, one layer, then the activation, which one do you want, and then another dense layer. And then before the classification, you need to have a softmax layer to perform the multi-class probability output generation. And don't forget, there's also an error layer or the loss layer if you're when you're doing the back propagation. You design that loss, but in our case, it's cross entropy loss. All right, so this almost solved the homework 4, but there are a lot of smaller things you can play with. The last year, there's a student got so much better than all the rest. So yeah, so very direct. So even though this is a very nicely almost overfitted data, but there's still a lot of things you can learn by doing this type of designs. Question about homework 4? Okay, so I did too careful review of CNN, but because I know this is a difficult month, so you're having a lot of other homeworks and also projects. So hopefully this type of detailed explanation can help you do the homework a little bit more efficient and learn a little bit better. Okay, so then people use CNN all over the place. The AlphaGo, which is the board, it's also used the CNN to perform prediction of values and prediction of actions. You can also, of course, use fully connected and multi-layer perceptron, but CNN actually performs better. The whole prediction can be, will a black win there or a white win there at that specific location, or actually the whole board, will the black win or will the white win? This can be a very intuitive prediction, right? Or they have a tie. So this is a very easy image classification. You can use CNN. So, and this is not a very big board too. It's just 19 times 19. And you can also use it to classify or recognize speech, the music, all this audio type of data classification or recognition. And it's, in the end, so now what you're performing is on a one-dimensional coordinate. So it's not because the audio is a one-dimensional signal, right? What you're applying is a sliding window only along this dimension. In the image case, you apply not only on the x-axis, you also move on the y-axis. Oh, actually, this one also moves on the y-axis because the frequency, they add an extra frequency dimension there. So you can perform the same thing as the CNN. In the image case, you move on the y spatial coordinate, and this one you move on the frequency coordinate. So CNN is almost everywhere. It's used for classification, image retrieval, object detection, pedestrian tracking, segmentation. It's just everywhere. And there's a really important trick. Make the CNN can be trained very, very, very deep. That's the residual trick. So I'm not going to read it carefully. Feel free to read it. And this is a very, very important trick, which makes the depth of the CNN networks start from, I think AlexNet was about 3, if I remember. Oh, actually very shallow. If I remember, 3 layers or 5 layers. Then go to 8 layers, and then 19 layers, 22 layers, and then this one is the ResNet with that residual trick is 152 layers. It's the one you just showed, convolution max pooling, but without that residual trick, you can't train that level of depth. It's a very important trick. All right, so it's an image roughly tell you the size. Yeah. Oh, it's not showing here. So there's a very blurred gray size. Just the VGG you might in the curves, they're trained models. They have different size of parameter size. I mean, this is the parameter size, this is like 150 megabytes, like VGG19. There's also another trick, is an inception trick. Inception trick, I think, is reduced the number of parameters pretty nicely. The reason that even though it's very, very deep, but the number of parameters actually is not that huge if you compare to the VGG19. So there are actually a lot of courses and also online blogs. Feel free to read it, and it's too much to cover in one lesson. And there's also another trick called adaptive or dynamic trick, and feel free to read it. Something called hyper network, Dyer network, split network, ADA network. There's so many. So the novelty here is this novel model design. Okay, so now let's go to, so that's the novelty there is in representation. And the next one is called a recurrent neural nets, neural networks, which is extremely important basic module for text analysis and or sequential type of data representation learning. So again, no details, and you can think about RNN models, model those dynamic temporal dependencies. It's really just a recurrence of the same operation to apply it again and again. And it's a very great approach before the BERT model. So actually now it's dominated as BERT model. So before the BERT model, this is called the seq-to-seq model. So this is one RNN model to model the Germany, the language conditional relationships. And this is the English, this is another RNN model to represent the conditional from awesome, then there's more likely to be sauce, that type of conditional relationships. So it had very good performance on machine translation, almost it was the state of the art. And now it was kind of replaced by some model called BERT model. So the recurrent neural networks is, you can think about the MLP is input, then hidden layer, then output. Then recurrent neural nets is input, then hidden, then go back to hidden, and then to many, many times, go to output. So I'm predicting the tth steps output based on t minus 1s. So you can think about this, it's a ht equivalent to some function is ht minus 1 and x. So it's a recurrent operation, right? We all know the function, recursive function is, I can then feed ht here to generate ht plus 1. And this really fits nicely to this type of sequential language representation. To represent this word, I have the x input, and then to represent the together, I use the representation from h1 and also current word to generate it together from a g function. And then for the next, I use the h2 to feed in this g function plus the current x3 and to generate h3. So this is what we meant a recurrent operation. And all those are the same function and the same set of parameters. All right, so and there's a lot of variation of the recurrent neural nets. It has one-to-one, one-to-many, many-to-one, many-to-many, and many to this is the machine translation, right? Many is in one space, and the other many is in another space. This is a Germany language space, and this is an English language space. They are not the same space. But you can have also the same space, right? Here, like the text input, and then I'm trying to generate maybe labeling, the labels of each word. Are they nouns or verbs? And this type of also work. It's the same space, but yeah, it's actually not the same space. That says, okay, maybe abstract generation. You're trying to summarize into summarization of article. They both, the input space, the English space, output space is also English space. All right, so there are many variations there. All right, so yeah, I already talked about it. So we normally call this part the encoder, and this part called the decoder. And sig-to-sig model is a very classic sequence encoder decoder formulation. I'm encoding all these input sentence. This is the encoder using RNN. I'm using this joint representation to generate its translated English translation. And this is a decoding step. All right. So there's also attention tricks, which I'm not going to cover. Feel free to read it. You're really trying to learn, not just treat them uniformly important. You're trying to learn which position is more important for the translation. How do you learn that importance? It's a technique called attention-based trick. They're also together with something called memory, and which try to free to read it. Like, so that's the CNN and RNN are both in the network topology novelty, right? And there's a very important novelty. It's actually in the loss formulation. It's this autoencoder decoder. In the end, it's really just a new loss formulation. So in fact, so let's go back to our block view. We normally think about what we learned. It's a feed forward, right? From input X all the way go to the loss function. There's only one direction, right? Feed forward. However, yeah, so this is actually the results. So you actually can not just all the way from input to output. You can equip the input to the hidden, then adding the hidden back to the input. So this is represented as this is the output, but actually in fact, I'm trying to predict back the input. So this loss is, I'm trying to guarantee the learned H can nicely recover the input. And this type of loss is very nice because even if you don't have Y output, you can only just use X itself to predict, to get good H. So this is the X, this is the H, let's just call that XQD. I want to make X and XQD very small. And this is one way to learn the H, right? And this is, in the end, if you think about it, this can be used to pre-train every layer here. If you know the middle, you can use it to train every layer by using the input as a guide signal. And this is the classic pre-training or pre-training trick or layer-wise pre-training trick. And it's really about this loss formulation. It's a new loss. And it changes the whole feed forward by adding the backward. This is actually a backward module. All right. So it's kind of getting tiring, but there are actually 18 to go. I'm going to do it really quickly. So the next trend is called memory neural networks. So it's really copied the ideas of human brain. So we normally have long-term memory and short-term memory, right? While you're doing on the go, doing a calculation, what you're using is the short-term memory. But if you want to do those very, the task has a lot of retrieval, your short-term memory is not enough, like this type of task. So I'm trying to ask the task very complicated. It's where's Joe? Where's the milk? Where was Joe before the office? You really have to memorize and also structure this whole paragraph to understand where's Joe? Where's the milk? was Joe before the office? This type of semantic task, there's no way actually you're just using your current where's Joe? How do you answer that? Extremely difficult. You have to organize this type of information in some kind of format, some kind of representation that helps you to answer the question needs very long-term history understanding. So for example, this one is a little bit shift is went to kitchen and then Joe pick up the milk and then Joe traveled to his office, Joe left the milk and Joe went to the bathroom. It's just, to be honest, even Earth, it's difficult to answer this type of questions. And people design something called explicit memory. And this is a classic network structure with neural nets. And then there's a memory representation to show that history and organize that history. I'm not going to talk about detail, and this paper is pretty classic called end-to-end memory networks. Yeah. Okay, there's too much to talk about, and then there are also multiple hops to understand the history. It's called multi-hop memory neural networks. How do you perform multiple hops of retrieval? Similar to what you're answering question, you retrieve your long-term memories. And then, so the trend 5 is, so there are a lot of data and their format is not this very regular image signal type. Images, to be honest, they are real values on a very regular structure, grid structure, right? It's a grid. And it's very nicely numerical values. So this is the image case, right? It's pretty regular. However, there's a lot of data like this, maybe the game or the computer programs. How can I make the computer to be able to generate a program that can calculate maybe 2 plus 3 equals to 5? I know this is extremely easy, but think about you're generating a network to perform this. You're not using arithmetic operation of the computer provided. You're generating a model to be able to do addition, to be able to do subtraction, to be able to do all the various arithmetic operations. How do you do that? And this input is extremely irregular, right? Extremely irregular. The output is also, the output in this case, maybe if you constrain it into operation of arithmetic, the operation is a little bit constrained, but input extremely irregular. How do you handle that? And how do you also handle this type of operation converted into a operation computer can directly work on, sum A and B? How do you do this? In the end, this is more like a program. I'm trying to learn a program, being able to write programs. All right, this is too late. Okay, so I think, let me do really quickly. So this is trend 6, is you can learn to optimize or learn to search. So how do you even know? This is exactly your question. How do I know what filter, how many filters, what's the size of the filters, what's the stride size? And that's all the questions currently, if you as a designer, you have to design all those and then just try an area. But there are something called neural architecture search, to provide a mechanism to search the number of filters, the filter height, the filter width, what's the stride height, and this is for the first layer. Then for the second layer, how do you search automatically using neural nets? So that's called neural architecture search. All right, so then trend 7. Okay, so the next trend is learning to learn or meta learning. So maybe let me skip this. This is a little bit too much, and you read, or maybe feel free to skip it. So the trend 8 is how do I represent, like I said, image is an extremely regular pattern, spatially regular pattern, right? But strings, graphs, sets, and the convolution design, what you use, like locality or translation invariance, they're not applicable on the graphs. And how do you design a neural net can learn representation of graph well, of tree well, of sets well? That's the variance 8. There are a lot of paper, and then generative GAN. So GAN is one of the breakthrough. In the end, there's a discriminator and then a generator, and I don't want to tell you the details because, but I just want to show you how amazing it really is. Okay, so like in this case, I'm feeding these GAN with a cartoon version of the image, then a celebrity regular image. It will generate the same style of the celebrity's image. Think about what is this intelligent task? This is extremely intelligent task, right? You're regenerating the images following that style. And that's why, again, it's really amazing. And there are some other things GAN can do. Okay, you can just do this kind of circle GAN, zebra, horse, zebra. Summer, the same image goes to the winter. Same image from winter goes to the summer. Or you have a bad resolution image, it can make it super. This is the original image. It can generate. I think this image is generated by GAN. Yeah, it's extremely detailed, fine resolution. And then one more. So you have input. This type of input is generating very realistic looking images. But think about this is how big this is for the design, for the artistic design industry, right? It's big, right? I mean, just animated type of input can generate this really realistic, very realistic images. One more. From edges to generate real looking bags. I think how important, how this revolutionized the fashion industry, right? And this is really big. That's why GAN is a revolutionary breakthrough. Okay, sorry, I'm going to use your 5 minutes, and there are actually two more trends. Actually, 3 trends. It's reinforcement learning, and one's reinforcement learning, AlphaGo and AlphaZero, and the last one is more adversary examples. Maybe you already learned about it. Feel free to read by yourself. And also bias in the deep learning models. So this one is very interesting, actually. Okay, so let's see. Even though they're great, but they are actually, in some cases, pretty stupid. This is starfish. It makes sense, right? But is this starfish? It's the pattern of starfish. So this can tell you something about CNN is learning. It's not the whole thing of fish. It learns something suboptimal. It learns in parts. Like this one, this is remote control. And this is electric guitar. All right? Okay, thank you. And then sorry, this is really long, but I think this is a fun lecture, so I'm